Hello everyone, welcome to lecture number 14 of CS531 Memory Systems and Architecture. So from last lecture we are discussing about cache partitioning. So in last lecture I have explained the basics of cache partitioning as well as the most well-known partitioning technique, that is UCP. I hope the concept of UCP is clear. So if the concept of UCP is not clear, then my advice will be, please watch my previous lecture first and then continue with this, because this is in this video, this lecture I will not explain the basics of cache partitioning that I have already explained. Also the concept that I will discuss today is based on UCP. In fact, most of the partitioning technique that we will discuss, that we will see in modern multiprocessors are based on UCP. Most of them are based on UCP. So please read the concept of UCP. So till now, whatever I explained in class, first I've explained replacement policy and then I'm explaining cache partitioning. So there are some concept which is required in every places. One is called DSS, dynamic set sampling, that will be applicable, that will be used in cache partitioning also. So you have to understand this, what is called DSS. In terms of parameters, I have maybe you can see most of the time we are using these terms mpki, cpi, and then there are some other terms called weighted speed up, ws, weighted speed up, then only speed up. Okay, only speed up. Then all these parameters you will find in the paper that I am discussing. In fact, if you want to know about these two terms, weighted paper, then read the paper, that our paper that we discussed, that is date paper of Kaushik, Prathamesh and me. You can read that paper to understand what is this WS speed up. In fact, I think WS speed up are also explained in the UCP paper that I have explained in last class. So these small concept will be required for this paper, for this course, as well as term paper. In fact, if you want to do further research, then also these concepts are required. Then I think some other concept like application behavior, what is called cache friendly application, non cache friendly application, then what is called scanning, right? And then thrashing, all these things are also important. I think I have used these terms multiple times in this course, so I hope it is clear to you. Regarding the speed of this course, I know I'm going little slow, but since this is an online mode, I don't want to give you much load, because if I'm giving you less load, don't what I'm expecting from your side is I'm expecting some honesty. Some honesty means you will spend some amount of time in this course. If you are thinking that the load of this course is less and you are spending more time on other course and you are completely ignoring this course, then this is your problem. Why this is your problem? Because if you are ignoring this course, I don't want you as a student for further research and all. You will just clear the course and I will forget you also. But my intention is to motivate some of you to do research in this area. So honestly speaking, if I give you more pressure, if I give you more force to love this course, that will not happen. Since term paper is officially not announced that you have to select your areas, but I hope you are working at least some, you are reading all these paper, because if you are reading these paper, then it will help you in term papers. The previously I was given a deadline that by this Friday you have to select the term paper, but there are some requests that please allow us to decide our term paper area by end of this month. So I have accepted this request, but it doesn't mean that you will start your term paper from by end of this March. You start it from now. You read papers. If you want to do it on replacement policy, read some paper from replacement policy. How to search new papers, I have already explained it to you. If you want to do term paper on partitioning, start reading more papers on partitioning. Just these three paper is not enough. Same thing is for prefetching. If you want to work, I have not discussed any more prefetching in more detail, but at least I think the basics of prefetching is explained. If you want to do work on DRAM based things or non-volatile memories, these are also, I think, non-volatile memory, some interesting works already explained at the beginning of this course. So you can start working in your term paper. And if you select your term paper by end of March, then definitely by mid of April, after 15 days only, I'll go for a group by group interview. Means how much your progress is, and that interview will be taken by me, not any other TAs. So there will be two status update. One is by 15th April and maybe another will be by end of April. So by end of April, I think there will be end sem. So before within the April, maybe I will ask you for two online meeting with each group to give the updates, because there is 30 marks and I have given you enough time. So what I can say, after mid sem you have to spend a lot of time on term paper. These are some. So coming back to today's lecture. So I hope the UCP concept is clear to you. So today we'll discuss a paper which is based on a limitation of UCP. So to understand this the limitation, I hope you need to understand some terms. There are some terms already written here. One more important term is dead block. I hope you remember what is called dead block. I've explained it many times when I was explaining replacement policy, right? Dead block means if a block is current a block, suppose you can say, suppose there is a block here, there is a block here. At any moment of time, you can say, suppose at this particular time, I can say, if I point here, so at this moment of time, whether the block is dead or not, that depends on from considering from this moment of time. If the block will not accessed by any core before eviction or before its eviction from the cache, then this block is called dead block. Okay. But suppose this at time t1 this block is access 1, then at time t2 this block is access again. So at this point, at this time, the block is not dead, because in future at t2 it will access. And suppose and this block is evicting from the cache here in suppose in t10, here the block is evicting. So at t1 the block is access here again, so it is not dead. But at after t2, at t2 here from this point, suppose this is t3, so from starting from t3 the block will not access, because block is evicting at t10 from the cache. So before evicting, it is in this time this is not accessing again, so during this time the block is called a dead block. So I hope at this point is clear. I have already explained you the dead block. Now if I go for the limitation of UCP, then let me explain you with just one set. Suppose this is a set and there are multiple ways are there in this set, and suppose this is how the ways is divided like 5,3. Suppose how many? 1 2 3 4 5 6 7 8. Okay. So there are 8 ways are there. 5,3 partitioning is 5,3. Partitioning is 5,3. Now it means that maximum at max how many blocks of suppose, and the same, if you remember my previous lecture, then assume that application a1 is running here, application a2 is running here, and 5,3 means a1 has 5 ways and a2 has 2 ways. So suppose and the blocks are like, suppose this is a1, this is a2, this is a1, a1, a2, a2, and a1, like this. Okay. But for simplicity I will not use this type of diagram. I will use a different diagram here. This is just for better understanding of you. So here I will use all the a1 in one side and all the a2 one side. a1, 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 and then a2, a2, a2. This is the actual one. This is just simple one, simplified version, because I am using it just to explain you the limitation of UCP in a better way. So now suppose there is a there is a borderline here, right? This is the border. Sorry, this is the border. This is the borderline. After this side is using by a1 and this side is using by a2. And how a UCP works, if you remember, this is the diagram of UCP. This is the same diagram of UCP paper, and I've written it, design it in a different way. So there are there are two cores, suppose the L1 and L2 cache, both are sharing a common last level cache as LLC, and both, if each core has their own utility monitoring circuit, this is called UMON. So here it is called UMON 1, in this side it is called UMON 2, and both captures the utility of the cache, what is called utility, that I have explained already. So now based on this utility information, these information are going here in this partitioning algo circuit, and this module is actually partitioning the cache either for 5 3 or so. So the complete process, suppose this is the partitioning this is the time, suppose let me explain it in this. Suppose this is a time t1, So from suppose T1 to T2, during this time the core will this utility module will collect information, and after this information, maybe here the partition will change. Okay, and now the partition is 5,3. Okay, now this time is called a fixed time period. Maybe this is called 5 million cycles, suppose. So again, once the partition has been decided 5,3, so this LLC will work as 5,3. This LLC will work as 5,3, but the humans are not ideal during this time. So now during the next 500 cycle here, during the next 500 cycle, 5 million cycles, sorry, the next 5 million cycles, human will again continuously collect information, and here at this time, suppose this is T3, in this time again partitioning will done, and after this, maybe for example, suppose the partition is changing from 5,3 to 3,5, and then from here, then the new partition will start working 3,5, and it will continue. So this is a periodic concept. Every after certain period of time, partition will change based on the information of human. Okay, so now there is a time, this time you can say, suppose partition period. I'm saying it as partition period because after this, so remember this term I'm writing here as partition period. Partition period. I don't think this is a standard term. I don't think. I assume that this is a term using by me. Partition period. Which one is partition period? Partition period means this 5 million. After this period, partition changes. So it means that once a partition is decided as 5,3, your partition will not change for partition period, for a particular partition during this partition period. After this partition period only, your partition will change. So now, a limitation of UCP is, there are two limitations. One is during this partition period, if the behavior of that application change. Suppose here I have given this is A1, right? This is A1 and this is A2. A1 has 5, A2 has 2 only. But the point I'm saying that at the during the partition period, if the behavior of A1 change and it is the utility of A1 became less and 5 is not required, then the partition will not change during this partition period. Partition will only change after that period. So that is the problem with, and how partition is handled in UCP. I think that part is I have already explained, but and I need to explain this part again, otherwise maybe you will find it difficulty. So let me explain how partition is maintained by UCP using this proper actual example. This is with the first example. So you can see here how many blocks of A1 are there. There are 5 blocks of A1 are there and 3 blocks of A2 are there. Now in this case, if there is another request came, suppose these are the requests. Suppose now a request of A1 came, then how many blocks of A1 are already here? 5 blocks are already there. Suppose the LRU blocks is this one. Now LRU block is this one. So if according to LRU policy you need to evict A2, and in place of A2 you need to insert this newly incoming block, but since according to partition you have to maintain 5,3, you cannot remove this LRU. Instead of this, you will remove the LRU from the A1 only. As for example, suppose LRU from the A1 is this, then you will remove this one, and in place of this A1 you will place the newly incoming A1 here. Why this? Because you have to maintain the partition of 5,3. So that's why I said in last class also, then once after the partition has been fixed, the rest of the thing is handled by replacement policy, that how to maintain the partition. Same thing, suppose now a block of A2 is coming, and in this case, suppose if this is the LRU, then no problem, we will remove A2 and we'll store the new A2 block here. But in somehow, suppose this block is now LRU and now a new A2 is coming, so you cannot replace this A1 to store A2, because if I remove this A1 and place this A2 here, then what will happen? The number of A2 blocks of A2 will be 4, which is not allowed. So this is how partition maintains. Okay, so now coming back to the limitation again, what I was saying, that in this situation here, if during a partition period, if the demand or the utility of this application changes, then UCP cannot handle it. That's the first one. Why cannot handle it? Because their partition is fixed. your partition cannot change. So in simplified version, this is same as this. So in simplified example, if I say this, so this, suppose this is your partition, means there are five ways here and three ways here. So the partition cannot deviate in UCP during partition period. That's why it is this is called it do not allow the deviation. This is a strict partition. So you can say it's not static partition, it's the dynamic partition, but it's just it is strict partition, means during the partition period you cannot change the partition. So but if there is some partitioning technique where during this partition period also it is deviation is allowed, means either the partition can deviate with this side or partition can some deviation is allowed, then this type of partition is called partition with deviation. So because of this is strict partition, one problem, as I said, that this type of problem can came the utility change. But maybe you can say that, sir, since we are changing it within 5 million cycles, so it is very rarely that within this partition period the utility of a block change, utility of an application change. So that is one point. But another limitation is related to dead blocks. It may be possible that one of the applications, suppose A1, after allocating V's or after allocating partition to it, maybe some of the blocks are dead here. Suppose these two blocks are dead. These two blocks are dead, and you will even there are many dead block detection techniques. Suppose I'm assuming that based on some detection technique, you can detect that these two blocks are dead. Even you detect that these two blocks are dead, if this application needs some more ways, you cannot allocate you cannot allocate these dead block to this particular application. But it should be done, right? Because these two blocks are dead, they are not using. So and if this application A2 is requiring more ways during a partition period, maybe we can remove this two dead block, and in this place maybe we can allow to store two blocks from A2. But if we do this, we are deviating the partition, right? It will not remain on 5.3, it will change. So that type of deviation is not allowed in UCP, but sometimes this deviation is very useful. So that's why what the paper that I will explain today is called PIPP. In short form, it's called PIPP. So remember this term. So every time when I say PIPP paper, you have to remember that I'm referring this particular paper. I'll discuss it. It's a paper proposed in 2009, I think, and it is proposed in ISCA. So let us go to this paper and try to quickly explain, because I no need to all the basic motivation I've already explained. So this is the paper. See, this is the short form of the paper. I'll use this PIPP. PIPP is the name of this short name of this paper, PIPP paper. I think it is published in ISCA 2009. See, it is published in ISCA 2009. So it is proposed almost 3 years after UCP proposed in 2006, and you can see the entire paper is based on UCP. Initially they are discussing all the concept of UCP, and then what are the limitation of UCP, and then they propose their own. So I'm kind of ignoring this initial content written, but I am advising you to read all this thing in one by one. If you are liking this subject, you are following my lectures, you will love to read this paper also, because you will understand all the concept written here. Nothing will be new for you. Okay, so see, these are way allocated kind of examples they have given. This type of examples I've already explained in my previous lecture when I was explaining UCP. And see here, if you go in section 2.2, then here they're explaining dead block management. This same thing, dead time means the dead block only, or similar thing. So they are explaining this same concept here that I've already explained in whiteboard. So I'm not repeating it, but I'm advising you to read all these things properly. Then only you will understand, then only you will love this paper. Because when I'm explaining, my explanation are not every time, it is not very standard, not very in a technical way. Sometimes I make things very simplified for you to understand. So that's why maybe whatever the way I am speaking, way I am explaining is not enough to do research. Why? Because my main intention here is to explain you the most basic concept of that paper. But I am doing this, I'm sometime I ignore some small concepts, small issues that how they are handling it. So for these you have to read the paper, you have to understand. Reading a paper, if you read a paper, then only you will understand the many small issues, how they are handling it, in fact how they are writing a paper, how to write your own proposal. All these things will be clear. See, in term paper, at least I'm expecting, not expecting that you will propose it, but what I said, that if you have proposed a good idea, then in summer after the course will complete the work and write a paper. In fact, when you'll go for MTP work, or you'll go, if you are a PhD student, when you'll go for research work, then you should know how to write a paper. So if you read a paper properly, then you'll understand that there is a basic way to write a paper: abstract, introduction, motivation. So, and what are the content written in each section by these famous authors. Then it will be very useful. And remember, the most of the paper that I am discussing here are from very top class conferences and journals. So that point is also you should remember. Okay, so and so I'm ignoring all this thing, and next they've explained here two concepts. It's called insertion and promotion for replacement policy. I don't think I need to explain it, what is called insertion and promotion policies, right? Many time I've explained it when I was discussing about replacement policy. That's why every class I repeat the 2 3 lines, that all the things are interrelated, right? Maybe why? Because I there is a point behind it, that if you are covering all this paper one by one, then you will understand that yes, they are actually interrelated. So starting to the main uh, concept of PIPP, it is starting from this section 3.2, basic PIPP. So here one more term is important, that this paper PIPP is proposing a partition is called pseudo partition. It's not a actual partition. Actual partition means the partition that I have shown here in UCP, that if there is a partition like 5,3, then it is strictly maintaining 5,3, and so that is called pure partitioning. But here there can pseudo partitioning. So pseudo partitioning means they are not strictly maintaining partition when by the replacement policy is not taking care every time that okay, I have to maintain 5 blocks from this application and 3 blocks from that application. They are not doing like this. So how their partitioning is doing? Their partitioning is doing based on by changing the policy of insertion and promotion of replacement. So pseudo partitioning techniques are more closely related with replacement policy than cache partitioning. That's why at the beginning of previous lecture I said that you cannot you can draw a line between cache partitioning and replacement. They are interrelated. So this PIPP is more replacement policy than cache partitioning, but yes, it is partitioning the cache. So that's why you call pseudo partitioning. How they did the partition? They did the partition by changing the insertion and promotion policy of the replacement policy. So now how they have changed the insertion promotion policy. So in PIPP, the architecture required is same as UCP. So if I go back to the diagram again here, so they are also using this diagram. They also need the human circuits, they all this thing, human circuit, and this what you can say, a partitioning algorithm. All these things are also there. And this output, that after some time after all this the partitioning algorithm is giving output as 5,3, okay, or 4,4, whatever be the partition output is giving by this partitioning algorithm, or suppose 4,4, this partitioning output is required in PIPP. So how PIPP works? So for PIPP to work, PIPP, first of all, PIPP need a partition. Suppose the 5,2 or 4,4 or 4,2 4 suppose 5,3, this type of partition is required. This type of partition is required. But based on this partition, how they are maintaining this partition, and from that point it is different from UCP. So how they are getting this partition? This is same as UCP. This part here, for this part, UCP is same as PIPP. Or basically you can say PIPP is using the concept of UCP only to find out the partition. That's why I said all these partition are based on UCP. Now if I go here again, how they did the partition. So suppose if we see here, they are, instead of two application, they are saying they have, this is generic, they have explained it in generic way. So they are saying that there are n parts, so there are n codes. So instead of 5,3, it will be divided into n ways, right? There are n partition. I explain it 5,3 assuming there are two applications, there are n applications. So 5.1, 5.2, 5n, these are the partition. So this partition will be divided by the same utility monitoring and all. So same as UCP. But once the partitioning is decided, how they are maintaining the partition is the next one. They are maintaining it like using insertion and promotion policy. How? Suppose this is the set. So 5 means every time the incoming blocks of application A1 will be inserted at the point, at the fifth position. Fifth position means, suppose this is your set. I think this also I have explained in last class. Suppose this is your set and this part is called MRU, I think, yes. And suppose this part is your LRU. So I think they are counting this like this, I think the positions are like 1 2 3 4 5 6 7 8. Suppose these are the positions. Partition is 5,3 means application of A1. Suppose A1 is related with 5 and A2 is related with 3. So whenever there is a block you need to insert from application 1, then it will be inserted at the fifth position always. Okay, and whenever we want to insert a block from A2, then it will be inserted at the this position. So this is their insertion policy. And promotion policy is every time there is a access, the promotion policy, it will be incremented +1 every time with high probability, and with low probability it will be remain same. So it is written here on a cache sheet. See, if you read from here, on a cache sheet, the promotion policy of for PIPB promotes the line by a single priority. It means that they will increment it, increment it in this line. It is 5, so if we promote it, then it will be here, right? Priority position with a probability of p rom. Okay, and the priority is unchanged with the probability of 1 minus p. So that with this probability p, they will change for every hit, they will change the priority they will increase the priority, or increase the this value. And increase this value means it will move towards MRU, and otherwise with the another probability they will keep it in the same position. So this is their promotion policy. And replacement policy, eviction policy, I think it is remains same. Every time a LRU block will be evicted. So this is how it is different from UCP. UCP says every time you cannot remove the LRU. I hope I have explained it right. If this by removing LRU, if the partition is not maintaining, then maybe you will not remove LRU, you will remove something else from the set. But here they are saying no, every time we'll remove LRU block, but we are changing the insertion policy, and insertion will be based on the partitioning values. Okay, so this is an example based on this one. And but in this example you can consider position. This is the LRU and this is the MRU one, and LRU is 1 and MRU is, I think, 1 2 3 4 5 6 7 8 is 8. Okay, and for this example they have used this as 1, means pre-rom as 1. So it means that every time we'll promote it, 1 minus pre-rom will be 0. And now consider this is the first case here. The next request is D. So what is the next request here? There are two applications assume here. One application is the block of one application are like this, a square shape, 1 2 3 4 5. These are the application of A1 suppose, and these black circles are blocks from A2 suppose. So the next request is coming from A2 because it's a circle, black circle, right? So to insert, where to insert it? If the partitioning is 5 3, you have to insert it the third position. Third position means we'll insert it in this position. Again, remember that here I am only explaining the LI means replacement circuit. We are not explaining the actual cache position. I hope this point I mentioned every time many time when I was discussing replacement policy, that this position that I'm inserting here doesn't mean that it is the actual way of set associative cache. This is a separate data structure maintained for replacement policy for each set, right? So here I'll insert D in this position. This is the third position, so D is inserted here, you can see. And which one will be removed? C will be removed, because every time we'll remove LRU. So all these will be shifted in one position, by one position, and D will be inserted in this third position. So this is the new case. At this state, if A1 is requesting for a block 6, this is the A1 request. So now where do we need to insert it? We need to insert it at the fifth position. So first of all, this block will be removed, everything will be shifted by one position, and then 1 2 3 4 5 in this fifth position. See, 6 is inserted. And then again, from this, if 7 is coming, then again everything will be removed, this B will be removed, and 7 will be inserted in sixth position. The entire example is like this only, you can check. So here I'll explain this situation. Suppose in this case a request for 2 comes, so it is a block from A1, right? So the block is already in the cache. See, the block is already, so it will be a hit. So if it is a hit, so it will be promoted by one position. So it is going here, see, it is going here to here, and E is going there. So it is promoted by one position. If again, so same thing for in this case D is excess, so D is promoted by one position. So this is how it is working. So remaining things are easy. So what I'm advising you, that try to understand this example by yourself, and this detailed example is also explained here in section 3.3. It is the complete example that I'm showing here. It is explained in more detail, so read it properly. So now if we if we see this example, most of the time they are maintaining the partition of 5 3. That means 5 for A1 and 3 for A2. Most of the time it is maintaining like this, but in some point it may deviate, and that they are actually means the trying to do when there is a requirement, when there is a demand for a particular application, it can deviate the partition as advised by the UCP monitors. Right. So here you can see these two lines, that in these two lines the partition is deviating, because in these two, okay, the partition is actually it is 7 2. It's not 5 sorry, it's not 5 3, it's 6 2, because there are 6 from A1 and only 2 from A2, right? And so in this case they are deviating, and for this deviation they are improving the performance. So that is the only difference. I think here also it is deviating, right? So here also it is deviating. It is also here, there is 6 from A1 and only 2 from A2. So this is their main concept. That's why it's called pseudo partitioning, because they are allowing deviation and they are not maintaining the partition. So this is their basic PIPP, and then if we go for next one, is called stream sensitive PIPP. Stream sensitive PIPP means if there are two applications, if I go here, I'll explain PIPP, stream sensitive PIPP here only. Suppose from A1 and A2, A1 is a streaming application or it's a scanning application, right? So in that case, if we are inserting at 5 position, then maybe it's not a correct one, because unnecessary we are giving more ways to a application which is not required, because scanning application means low utility application, right? Low utility, what is called low utility, that I've explained in last lecture. So low utility application, for low utility application here, if you give more ways, then it's a wastage of ways. So in that case, if some of the application has scanning behavior, then how to change the insertion policies, that is explained in this section. I am not explaining this section here, because if you understand till this point, then you can easily understand after this. But this stream sensitive PIPP is a part of your course, you have to understand it. This you have to read it properly, and then what I'm expecting from you, that you will read this paper till this point properly, and you have to understand the concept, what they are saying about PIPP. Okay, so that's it from PIPP paper. Now in this lecture, let me explain another interesting paper, which is designed on top of PIPP. So this paper is this I am also a part of this paper. So the first author is Pratik, and the last author is the Hemangi Kapoor, the professor of IIT Guwahati. So this paper is going towards a better cache utilization using control cache partitioning. In short, we call it CACIP. Sorry, this name of this paper is not CACIP. The short name is CCPIP. Cache control. Sorry, it is CCPIP. So every time when I'll say ccpip, then pip, then you have to understand that I'm referring this paper ccpip. So I'll only explain how this paper is different from PIPP. Remaining things I'll not explain. I'm expecting that you will read the paper and understand it. So when you read the paper, you will see this. Now the experiment of this paper is done with not just two core here. There are four cores for the use for this experiments, but I'll not explain this paper in detail. So most of the things written here is I think it will be familiar to you. You can see there is an example here similar to PIPP, but this example I think shows that how it is different from example of PIPP, and it's uncontrolled stealing. So uncontrolled stealing is the main concept here that this paper is addressed, and this paper is addressed. So uncontrolled stealing means in PIPP what we said, suppose this is a set. If this is your set and suppose 1 2 3 4 5 6 7 8, so 1, let me make it 8 way set associative cache, and suppose the partition is 5 comma 3. So what it is saying PIPP that it can deviate from this partition, right? This is the main concept of PIPP. It can deviate, but there is a problem with deviation also. So and that problem is at, and in worst case it can deviate the entire thing. So suppose this is a1 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 and a1, and in ideal case that it should be 3a2 should be there, but as I said that it can deviate. So suppose it is deviating, and this is also a1 and this is also a1, suppose. Okay, so this is allowed in PIPP, right? This is allowed in PIPP. But the problem with PIPP that since there is no control of deviation, it may be possible that this also become a1. In that case, the entire cache is now means used by a1 only, and a2 has no use. It may be possible, and in that case one of the application may be stopped. In that case a2 is starving, right? So this type of situation may arise in PIPP, and that's why this we propose CCPIP. In CCPIP what is happening, this type of deviation is not allowing, means the deviation is controlled deviation. Controlled deviation means when we are deviating, we will take care that one application cannot remove all the partitions from other application, any other application, and that is the main concept of CCPIP. So I will not explain CCPIP in more detail. Remaining things, it's easy, you can directly read it from the paper, and this main concept that is this only, but let me explain it again, that in PIPP you can, since deviation is allowed, in worst case it may be possible that all the ways are taken by one application. In that case another application will become starved, and that is handled in CCPIP. In CCPIP the deviation is a controlled deviation, means when we are deviating we'll allow deviation, but the deviation will not be like it completely you taking all the ways from any other application. So that is controlled in CCPIP, and remaining things are is simple, easy to understand. So I am not explaining all these things, but what I am expecting from your side, same is the other papers, that you will read till the experimental section up to this part, and if anything is not clear, let me know. So that's it from CCPIP. Remaining things, you read the paper, you'll understand some more concept that is written in this paper. So I think this week I have already given you 3 papers for study: UCP, PIPP and CCPIP. So read this 3 paper properly. This is part of your exam. And one more lecture that I will upload in this week. In that lecture I will also discuss concept about cache partitioning, but those concept I think I'll not force you to read for your exam. The concept may be helpful for your term paper, but I'll discuss this I'll not discuss it in terms of your exam. Okay, and but if you see the paper that I've explained from for cache partitioning, I'm starting from 2006 and I'm finishing with 2013. So so it means that I have not discussed the most means recent partitioning technique yet. So that's why I'll try to cover some recent partitioning technique in next lecture, but this will be only helpful for your term paper. So this is a paper, this is delta distributed locality aware cache partitioning for tile based chip multiprocessor. So this is a cache partitioning technique proposed for tile based chip multiprocessor. So I hope you know what is called tile based chip multiprocessor, right? Tile based chip multiprocessor means TCMP, and I've shown you a diagram of TCMP in many lectures. So this is a very recent paper, very interesting paper. It is proposed, it is published in just last year 2020. So I'll try to explain this paper in next week, so that you'll get some idea that how cache partitioning techniques are using in modern days. So, and my one more intention, every time when I'm discussing some paper, that try to show you some relation from the old paper to the new papers. That's why the replacement I started from 2007 and I explained till 2017, right? And here I'm partitioning also, I've started from 2006 and I'll explain till 2020, sorry. So in this way, you will get an idea that how this partitioning requirement are changed, and even at today how the area is still open, and how you can work on this area. Otherwise you may think that okay, partitioning started from 2006, so there is nothing to do at this in 2021, but it's not like this. Even today also you can do some interesting work in this. Because why? Because architectures are changing. All the concept when discussing like UCP, PIPP, CCIP, at that when I discuss all this technique, I have not explained anything related to TCMP, right? And there was no concept of TCMP also. Those are based on the classic multi-core architecture, right? So nowadays the LLC is already divided into multiple banks, and they are distributed among multiple tiles. So in this scenario, how the cache partitioning will work? Does the old UCP based partitioning will perfectly work here, or there will be some more limits, some challenges to implement them in new architectures? So all these things are important. Application demands are increasing, right? Different prefetching techniques are coming. So all the based on all these things, how your partitioning should change and all. So it will be only clear when you read more papers about partitioning. And since in this course I cannot teach you lot of papers, and I cannot say that you have to read all these papers, and I'll ask question from all this paper in exam, that I cannot tell, because otherwise there will be no limit of this course. So for exam purpose I am giving you limited paper, but if you want to know more about this, if you want to do research in this area, you have to search more paper, you have to search more paper, you have to read more paper on partitioning. Then only everything will be clear to you. So I think in next class I'll explain this paper, and I'll try to cover some more partitioning based paper in short. And in short I'll explain. So at the end I'm again reminding that start working for your term paper. Maybe you will decide your area on 30th March, but it's not like that. By 29th March you will start thinking, and by 30th March you will decide your area of your term paper. So now from now onwards you start thinking about the term paper, and on 30th by 30th March you have to decide your term paper. Okay, one more important point is the mid-sem quiz. That is the mandatory quiz. So the mandatory quiz date, I think I'm planning it on either 25th or 26th. So and Google Classroom, I'll separately post a comment there that either 25th or 26th, and I'll wait for one or 2 day if you have any complaint. And by this, so I'll fix the date. So the syllabus of mid-sem will be till this cache partitioning. Till cache partitioning you have to clear, and then whatever I'll explain after, basically whatever I'll explain after today's class will not be included in midsem. Thank you for watching this video. See you in next video.